Everybody, let's spend a little bit of time talking about some deeper gas laws. Some of the gas laws that we've already done may have been a little more straightforward. And so this video is going to talk about effusion, not to be confused with diffusion, okay? And so effusion is a property of gas that has to do with the molecules traveling through a pin-sized hole, or a really, really tiny hole. Let me get rid of my face here, and then we can go to slide number 3 here. Okay, so here's what effusion is. Okay, I define it here, and that's what I said. But a practical explanation for what effusion is the reason why a latex balloon deflates. Okay, so we have the same, in essence, the same latex balloon here, but one is filled with pure nitrogen and one is filled with pure helium. What's the difference between the two? Well, the difference is that this balloon is filled with N2, which has a molar mass of 28, and this balloon is filled with helium, which has a molar mass of 4. Which one is bigger? Right, the nitrogen. That's a bigger molecule. Okay, and what we may not know is that latex isn't as smooth as we think it is. And so latex is made up of these big long chains of molecules that come together, but they kind of are woven together in all sorts of patterns. But you'll notice, and I'll do this in red, that there can be holes in the latex. So what will happen is, over time, all the gas will effuse through the latex, but the smaller one will effuse more quickly because the smaller one can get out of the hole, or even more holes, more quickly, okay? Because those molecules are moving. Okay, and so this was, or is called, Graham's law of effusion. Graham's law of effusion, and let me correct something here. This just says that the rate of effusion, and this should be, is proportional to, okay? It's not equal to 1 over the square root of molar mass, but is proportional to the square root of molar mass. Okay. Now, the way that we usually apply this is we will say that the rate of effusion of the first gas divided by the rate of the effusion of a second gas is equal to the molar mass, the square root of the molar mass of gas 2 over the molar mass of gas 1. So this is kind of the practical application of effusion. Okay. Yeah, so let's do a sample problem here. So you can read this, and it talks about 2 gases. And the idea here is that you can set up an experiment to determine the molar mass of a gas through an effusion setup. And so I know it sounds weird, but you can actually measure the rate of effusion I don't know, pretty easily. Not easily, but it's something we can do in the lab. Okay, I did it as an undergraduate when I was in Dr. Peipel's class, of all things. It's a physical chemistry thing. So, well, let's get started. What we know is Graham's law of effusion says that the rate of effusion of gas 1 divided by the rate of effusion of gas 2 is equal to the square root, and I'm going to abbreviate this. The symbol for molar mass, which we may not know, is kind of a script capital M. And so that's the square root of 2 over the script capital M1. And so now it's just a matter of kind of plugging in and making sure that we keep rate 1 and molar mass 1 the same, okay, and in the right spot. So this is going to go to, so I'm going to call this tetrafluoroethylene. I'm going to call that 1, okay, and we're given a rate of, so this is 4 times 10 to the minus 6 moles per hour divided by, okay, some compound that we don't know, so this is kind of the unknown, 5.8 times 10 to the minus 6 moles per hour. And that's going to equal the square root of the molar masses. Here's the thing, we don't know what the molar mass of the unknown is, molar mass here, but we can calculate the molar mass of tetrafluoroethylene. And so tetrafluoroethylene, let's see, C2H, so this is C is equal to 2 times 12, okay, and fluorine, there's 4 of them, that's 4 times 19. So I'm going to I'm going to get my calculator here. So let's turn this guy on. Let's clear out my work. And so this is going to be 2 times 12 plus 4 times 19. And that's going to give us the molar mass of, oh look, it's 100. Okay, so now we can do math. We can do some math. So we're going to go 4 times 10 to the, make sure you put that in correctly, to the negative 6 divided by 5.8 times 10 to the negative 6. So this side is equal to, this is 0.6897. Okay, I'm just using 4 significant figures. And that equals the square root of the molar mass of 2 over 10. Remember, when you have the square root of a fraction, it's equivalent to the square root of that and the square root of that. So we're going to multiply by 10. Okay, so we're going to go times 10. And then we're going to take that value to get rid of the squared. We're going to, or get rid of the square root, we're going to have to square it. So now we're going to take that and we're going to square the, not square root, we're going to square the answer. And when we get that answer, now we get an answer of 47.56 grams per mole for that molar mass. Now, if we really wanted to impress, what we could do is we could try to figure out what the reasonable formula for this compound is. Okay, and so let's see, boron and hydrogen. Well, boron has a molar mass of 10.8. Okay, so we know we can't have any more than 5. We can't have 5. So we have to have 4, 3, 2, or 1 borons, because 5 times this. Let me get rid of some of this here. Okay, so we have a molar mass of 47.56 grams per mole, and we know that we have to have boron and hydrogen. Boron has a molar mass of 10.81. And so if we have 5 times 10.81, and I'm not trying to insult your intelligence, but I'm just saying, so that can't be that. Okay, but we can definitely have 4 times 10.81. And when we do that, we get 43.24. That's pretty good. Okay, what if we have 3? 3 times 10.81. Okay, so we're either going to have 4, which is going to give us 43.24. Now the problem isn't asking for us to do this. I'm just showing you how to do it. Or 3 of these at 32.43. Now, if we have 32 of these, or if we have 3 of these, that means the rest of the mass has to be hydrogen. So if we have that, that's going to be how many hydrogens? Because each hydrogen has a mass of 1 about. So this is going to be about, well, that's 32.5. So this is going to be about 15. So if it's this, it's going to be 15 hydrogens. So 3 with 15 hydrogens doesn't seem probably like the best. 3 borons with 15 hydrogens. Okay, but now if we have 4 borons, that means we have 4 hydrogens, and that makes a lot more sense that it's B4H4. Okay, so that is our empirical formula, or that's our molecular formula there. And we figured that out just based on doing an effusion exercise. Okay, Let's do another sample problem about effusion. And so this is more of a multiple choice thing here. So I'm going to get rid of my calculator. And you can see here that the question is, which one is going to effuse faster? Well, the ones that effuse faster are the ones that weigh less. So it's really just a matter of calculating molar mass and going from there. So carbon dioxide is 44 and fluorine is 38. So guess what? Fluorine is going to effuse faster. This is 32. This is 28. So this one is going to effuse faster. Okay, this one is going to effuse faster. Now I can do that very quickly because it's C2H4 versus C2H6. This has more hydrogens. Okay, and now this one here, we can do the molar mass. So this is 12 plus 19 plus 3. There's 3 chlorines, 35.45. And then this one is going to be excuse me, 2 times 12 plus 2 times 35.45 plus 4 times 19. So my guess is that this guy is going to effuse faster, okay, because it is has the smaller molar mass. So those are sample effusion problems. Yeah, that was crazy. Okay, those are sample effusion problems, and hope this helps out with effusion. Have a great day.